Well, it's 4 o'clock. Guess it's time to get started. Welcome. My name is George. Today I'm joined by Sam, Ben, Lauren, Jesse, and Justin. We are Team SHAMU, and this is our critical design review. SHAMU's project is to create an unmanned aerial vehicle that will be capable of carrying a payload that will be capable of locating sperm whales. This vehicle will be deployed from a vessel's helipad. This is the end of the year or multi-year ConOps. This is what the end project is going to look like, but please notice we are only doing the objects listed here in blue, and we are not locating whales this semester. Instead, this is our ConOps. So we'll be doing the same 6 items as pointed out before: transport, assemble, flight checks, launch, mission, land, turnaround. The project will be transported and assembled at our testing site, which will be simulated here with our helipad, after which we do our pre-flight checks and fly out the aircraft 12 kilometers to test our 12-kilometer communication range. We'll have it fly back and complete a 100-kilometer range in this figure 8 motion, after which the vehicle will be recovered. We'll swipe out the data and the battery, disassemble it, and return home for the day. These are our functional block requirements. First off, our vehicle must have a manually piloted mode with autonomous mode at cruise. It must be able to take off and land from a 9.1 meter by 9.1 meter platform. It must have a 12-kilometer communication range. It must also support a downward-facing payload and must be operable and recoverable up to 10 meters per second in winds, and must have a 100-kilometer ground track range endurance.
All right, now I will be discussing our design solutions. Here's a list of our different subsystems with their associated design solutions. And here's a functional block diagram of our system. Please take note of the legend in the bottom left, and yellow is what we'll be designing, and blue is what we'll be acquiring. The main components of this functional block diagram are the ground control station and the UAV. The ground control station consists of a radio stack and a laptop, and the UAV consists of a radio stack, flight computer, autopilot, and a simulated sensor payload. The main lines of communication between the ground control station and the UAV are a 433 megahertz channel and a 900 megahertz channel. Now moving on to our aircraft design solution. On the right is 3 views of SHAMU's UAV. And after our design and analysis, we've come up with these parameters. Some of the more notable ones are the 3-meter wingspan, a gross weight of 8.45 kilograms, a cruise speed of 20 meters per second, and a cruise L over D between 12 and 16.2. Now please note that this minimum L over D of 12 is what's required to achieve the 100-kilometer ground track range with the chosen battery. On the right is a SolidWorks rendering of SHAMU's UAV. The fuselage will be made out of a foam fiberglass composite, and the nose will be left uncovered to take the compressive forces of landing. Each wing half will be made of foam with an interior carbon fiber spar and will be covered with a plastic coating for aerodynamic efficiency. Now for the takeoff system, our takeoff design solution is shown here in the top right. It's a rail system with a dolly, and it's powered by bungees. Notice the dolly here in the bottom right. And how it works together is the dolly sits on top of the rail system. The UAV is loaded into the dolly. The bungees are mounted, they're staked into the ground 1 meter in front of the system. And the UAV is accelerated from 0 to 13.2 meters per second in just under 0.7 seconds. For our recovery system, we went with a net. It's shown on the right with these given dimensions. Upon impact with the net will collapse around the UAV. The lines will extend through the pulleys, and this will in turn extend our dampening system, which consists of 2 bungees that are anchored here. We're also utilizing a sailing cleat so that once the bungees are fully extended, they do not rebound back, throwing the UAV out of the net. For redundancy, we're also using a nose hook on the nose of the aircraft that will hook into the gauge of the net and will not allow the UAV to be ejected. Our autopilot flight computer and communication design solution is shown in this block diagram. Please notice the legend in the bottom left. Software that we'll be writing is in yellow, software that's existing is in blue, and off-the-shelf hardware is in purple. The main components here are the ground control station and the UAV. Controls will be inputted into a control radio and sent to the UAV via a 433 megahertz channel. They will be accepted by the autopilot, which is in control of the control surfaces and the propulsion system of the UAV. Telemetry will be sent to the flight computer. This will be packed up with image data and sent back via a 900 megahertz channel to the ground station. Finally, our electronics design solution. Here's a list of our chosen electronic components. All were chosen based on fulfilling our design requirements. I will highlight one here, which is our 22,000 milliamp hour lithium polymer battery. This was chosen once again to fulfill our 100 kilometer ground track range. Now for our critical project elements. Our first one is aerial vehicle design, and the associated requirements are to have stability and control throughout the mission and to accommodate a future sensor payload. Our next CPE is takeoff and recovery. The requirement considerations for this CPE are to accelerate and decelerate the aircraft under its maximum structural load limit and to do so on a 9 by 9 meter helipad. Our third CPE is to communicate with the ground station, and the main requirement for this is to do so at 12 kilometers range, as we showed in the ConOps. And our final CPE is our flight computer and autopilot, and the main requirements for this CPE are to collect sensor data for the virtual cockpit to aid the pilot in flying the UAV and to keep the aircraft in steady level flight.
All right, I'll be discussing the design requirement satisfaction, and in particular I'll be covering the airframe and the power plant. So I'll be covering functional requirements 1, 2, 4, 6, and all of the associated derived requirements. So First one is the functional requirement 4. The aircraft supports downward-facing 2 kilogram simulated instrument payload with these dimensions listed here. Shown in the center is a SolidWorks image of the removable payload bay, and right here is the downward-facing Raspberry Pi cam mount. Located behind that is going to be the ballast mount, where the ballast for the 2 kilogram requirement will be located. Please note that the 11 centimeter height on this removable section is less than the 15 centimeter requirement here, and the reason for that is the full assembly, the walls and the fuselage right here will have a 15 centimeter height, therefore achieving that requirement. So functional requirement 4 has been satisfied. Next, drive requirement 1.1. The aircraft shall have static longitudinal stability. Shown on the right here is a side view of our aircraft with the center of gravity and the aerodynamic center labeled. The aerodynamic center is approximately 71 centimeters behind the nose and was calculated using AAA, and it accounts for wings and fuselage effects. The CG is at approximately 65 centimeters behind the nose and was calculated using SolidWorks. This gives us a static margin of approximately 22%. Therefore, derived requirement 1.1 is satisfied. Next, drive requirement 6.1, the aircraft shall have a lift-to-drag ratio of 12. Shown on the left here is an analytical model that shows the relationship between the lift over drag and the cruise velocity. With our aircraft at a cruise velocity of 20 meters per second, this model predicts a lift over drag of 16.2. We also ran aerodynamic simulation using some software available online, such as AVL and XFlyer, and they all predicted L over Ds greater than 12. Please note in the future we'll be verifying the L over D of our aircraft using a half-scale model, and we will be performing a glide test to verify that. Therefore, derived requirement 6.1 has been satisfied. Now, derived requirement 6.2, battery shall have a 1.4 hour endurance. On the left here is the power requirements for all of the main components of our aircraft. And if you look at the motor, there's two phases of the flight. There's steady flight, where the assumption is the thrust is equal to the drag experienced. And then during climb, where we have a climb rate of approximately 7 meters per second, yielding this power needed. And then this total energy requires 375 watts. Our battery will provide 375 watt hours, and then the battery will provide 390 watt hours, therefore derived requirement 6.2 is satisfied. Next, derived requirement 2.1. the aircraft shall have a nose hook that sustains 5G landing forces. On the left here is a CAD rendering of the nose hook assembly, and you'll see these 4 prongs coming out from the nose. If you were to connect the endpoints of each of these prongs, it would form a square that has the same size gauge as the recovery net, and so it'll basically just fit right into there. And supported by this threaded rod hub that passes through the nose cone of the fuselage. We performed a structural analysis on the hook, and for that we looked at the worst case scenario, which was basically one of the prongs taking all of the load, which would be 5G, and that resulted in a bending moment of 37 Newton meters. And then for our dimensions, that results in internal stress of 766 megapascals. We chose titanium for this, which has a tensile strength of 880 megapascals. Therefore, derived requirement 2.1 has been satisfied. And before we move on, please note that we did a test before this with a separate, similarly designed hook and had an 88% success rate. And the improvements that we've made to this design will improve upon that success rate. Derived requirement 2.2, the aircraft wing shall sustain 5G forces for maneuvers and net recovery. What's circled here in blue is the rod that connects the wings to the fuselage, and this was done because the wings need to be removed from the aircraft for transportation of the aircraft. And so what's shown here is the wing rib, and that's what's actually connecting the two via the rod. And then here's a free body diagram below. The forces downward is the weight of the aircraft, and then lift going upwards. Note these thin vertical lines right here. That represents these green wing ribs shown here. Based off of this analysis, we have a shear force of 103.5 newtons, and for a 3/16 diameter rod, that's a shear stress of 5.65 megapascals. We chose aluminum for this rod, which has a shear strength of 204 megapascals. Therefore, this portion of derived requirement 2.2 has been satisfied. Same derived requirement, we're just looking at a different portion of the wing now. We're going to be looking at the carbon fiber rod, or the spar, excuse me, and then also the aluminum carry-through rod right here. This was modeled as a cantilever beam with a evenly distributed 5G loading. This resulted in a bending moment of 116 Newton meters, shear force of 169 newtons, and then for our dimensions, internal stress of 430 megapascals, shear stress of 2.8 megapascals. And considering that this is carbon fiber, the tensile strength and the shear strength is greater than the stresses experienced. And then we performed a similar type of analysis for the aluminum carry-through rod, and we found that the tensile strength of aluminum is greater than the stresses experienced. Therefore, derived requirement 2.2 has been satisfied. Now we're looking at derived requirement 1.2. The control system shall provide required control surface deflections for aircraft longitudinal and lateral stability throughout all phases of autonomous flight. What's shown here is the controllability matrices for our system, both the longitudinal and the lateral. And this shows how they were formed using the A and B states matrices from the state space model for our system. And we used AVL to calculate the state space matrices. And what these matrices actually contain, for instance, this, the A matrix that contains the coefficients of the linearized equations of motion for either the longitudinal or the lateral dynamics. And then the B matrix shows how the control inputs affects the states in the state space model. And the significance of this is we showed that it was both controllability matrices were full rank, and that means that we can use our elevon deflections to modify the poles for any desired stability that we would like. Therefore, derived requirement 1.2 has been satisfied. In conclusion, the previous slide showed how our aerial vehicle design fulfills functional requirements 1, 2, 4, 6, and all of the associated derived requirements.
Moving on to the launch system. So the driving design requirements behind the launch system were functional requirement 2 and its associated derived requirements. Functional requirement 2 is to take off and land from our 9.1 meter by 9.1 meter platform obstructed fore and aft. Our rail system length is 5.8 meters and it is 2.4 meters wide with a 1.1 meter anchor forward of the rail. That satisfies our total length requirement being under 9.1 meters. The derived requirements are to launch the system to 13.2 meters per second before the end of the rail, and also have the aircraft sustain under 5 Gs. As you can see here on the left with our calculations for energy and force, the UAV will reach a speed of 13.2 meters per second at 4 meters, which is less than the 5.25 meters ramp length, and the UAV in cradle experiences 1.9 Gs throughout the launch, satisfying both of our derived requirements. So in conclusion, for the launch system, both functional requirement 2 and its associated derived requirements have been met. Next is the recovery system. Similar to the launch system, the recovery system driving design requirement was functional requirement 2 and its associated derived requirements. Please take note that the net is 7.6 meters wide, which is more than double the wingspan of our aircraft. The recovery system requirements are to capture the aircraft at 572 joules of kinetic energy, factoring out because of our 9.1 kilogram mass at a 12 meters per second approach speed. Each of the bungees holds 1/2 of the potential energy once the kinetic energy has been stopped. That factors out to a 2.2 meter extension and a 4.8 meter total recovery distance, satisfying functional requirement 2 by keeping it under 9.1 meters. Functional requirement 2, again, is keep the system within the 9.1 meter by 9.1 meter platform, obstructed fore and aft. The recovery system dimensions on the ground are 7.6 meters by 3.0 meters, which fits within our requirement. And the maximum line tension on the aircraft at full extension is 130 newtons. That factors out to 395 total newtons on the aircraft at the end of the landing, which ends up being 4.4 Gs, which is less than our 5 G requirement, satisfying derived requirement 2.1. The final requirement is that the capture system itself be able to sustain the 5 G landing forces. Now, the primary failure mode here was bending at the uppermost post, at the uppermost support on one of the posts. With each of the lines holding 130 newtons, that gives us a 555 newton meter bending moment at the post, and our 9 centimeter outer 7.6 centimeter inner diameter PVC pipe gives us a 17.5 MPa bending stress, which is less than the 34 MPa allowable for the tensile strength of PVC, satisfying derived requirement 2.2. So in conclusion, the recovery system has also satisfied functional requirement 2 and its associated derived requirements.
So the navigation and communication subsystem is geared towards satisfying functional requirement 1 and 3, which are to operate in manually piloted mode throughout all phases of flight with autonomous mode capability at cruise altitude, and 12-kilometer communication range for telemetry, images, and RC control from the ground station. So the telemetry is handled by a 900 megahertz data link channel, and attitude is provided by the Pixhawk 2.1 running PX4 Pro. Positions provided by the onboard here plus GPS along with the system status. Telemetry is sent over Mavlink connection to the ground station, which requires 17.5 kilobits per second data rate, and we have an available 112.5, thus satisfying requirement 1.1, drive requirement. And virtual cockpit provided by Q Ground Control will be responsible for providing the pilot with the necessary instrumentation to fly in manual mode. It provides a digital 6-pack, moving map display, and battery monitoring. Its interface is shown over here to the right. And that satisfies derived requirement 1.2. Image transmission is to be accomplished with MavImage, which is responsible for capturing and sending and receiving the images in coordination with what we call Mav tables, which is Mavlink's protocol for routing the image packets through the telemetry link. And that satisfies derived requirement 3.2. So the Pixhawk 2.1 autopilot running PX4 Pro flies autonomous missions based on a flight plan consisting of waypoints. It's reprogrammable during flight in loiter mode, thus satisfying derived requirement 1.3. Q ground control, as shown to the right over here, has a flight plan creation and upload. With our data rate, we can get 330 waypoints per second, so that satisfies derived requirement 1.4. So in order to analyze the feasibility of the comm system to satisfy the 12-kilometer range requirement, a link budget was made to model that feasibility under the worst case scenario, with the gains and losses of each associated component being maximized for the lowest gains and the highest possible losses, which gives us the most conservative estimate possible, which results in a link margin of about 3.59 decibels, which is small, so a range test is definitely needed to qualify the communications requirement, but for now, derived requirement 3.1 is satisfied. So in conclusion, the previous slide have showed how functional requirement 1 and 3 have both been satisfied.
All right, now I'll discuss project risks. We've compiled a list of potential risks for our project shown in this table here, along with their pre-mitigation, likelihood, and impact. Please note this is not a fraction. This is a likelihood score and an impact score pre-mitigation, a mitigation plan, and a post-mitigation likelihood and impact score. The ones highlighted in here are ones we consider to be significant risks. I'll talk about number 2 here, which is a communication system failure during a flight test. The reason this got such a high likelihood score is because we'll be writing our own software to aid the communication system, and it will need an extensive testing before being integrated with the UAV. And the impact score is so high because if we're at 12 kilometers and we lose communication, there's serious risk of loss of vehicle there. After testing and engaging the autopilot failsafe mode, the likelihood and impact score will decrease significantly. One more I'd like to discuss here is the project running over budget. Our mitigation plan for this is to follow our detailed budget plan that we've laid out at this point, and also to conduct extensive half-scale testing on our half-scale model to work out any details and fix any issues before we build the full-scale model and fly it for the first time. Here you can see our pre-mitigation risk matrix, and after we apply our mitigation plan, we move out of the high-risk zone here, and we still have a few moderate risks here, and we'll be keeping these in mind as we move forward.
We have created a full testing plan. However, I will go over the 5 tests that we view most crucial to verifying our CPEs. First, we would like to validate our stability model. This test will be done with our half-scale model controlled by a pilot with an accelerometer on board. The accelerometer will track the motion of the half-scale model and verify that we can apply the same fidelity of our stability model to our full-scale UAV. Next, we would like to validate our speed for our launch model. This will involve our full-scale launching system with a dummy mass the weight of the UAV and a camera to record a simulated launch. The frames from the video will be placed into Logger Pro, where we can validate that our launch system reaches the necessary 13.2 meters per second we need for launch. Next, we would like to validate the forces felt by our UAV upon recovery. We will perform this test by having our full-scale capture system with a dummy mass, again the weight of our UAV, with an accelerometer. The accelerometer will verify the forces felt on the dummy mass upon capture. And we will use a high-speed camera as a backup to verify the extension by the net and the speed felt by the dummy mass. Next, we would like to validate our range model. This can be done with a communications range test. In this test, we will place our 2 radios at our 12-kilometer distance, along with our antennas. We will verify that we can send and receive an image with our mission gains. Finally, we would like to verify our endurance. We can do this with a battery power test. In this test, we will place a simulated mission load of our motor, our autopilot, and our flight computer onto a battery. We will then run the battery for a simulated mission with climb and cruise. During this test, we will monitor the voltage of the battery and ensure that the battery does not reach cutoff voltage during our simulated mission. In conclusion, we will be able to verify our requirements and validate our models for stability, launch recovery, endurance, and range with these tests.
We'll finish up with SHAMU's project planning for the future. So this is our organizational chart. At the top, we have our customer, John Coster, and our advisor, Donna Guerin. Below is our hierarchy, where we have a project manager, a system engineer, and our various technical leads, as well as the names associated with those leads. This is our work breakdown structure. As you can see, items completed in green have been done for this semester, while items yet to be completed in beige will be done in this upcoming semester. Here's our test plan. It just shows how tests will start to flow into each other. Items in blue are tests that can be done independent of other subsystems. The tests in red are essentially our integration tests, where each subsystem will combine their results into a new test. And then our yellow line here marks the test readiness review date. So items before the test readiness review will be completed by then, and then items afterwards will be completed afterwards. This is our schedule in the form of a Gantt chart. Items in the darker blue are our planned schedule for those tasks, and then the light blue marks the margin we've placed for those tasks. Here you can see our critical path. Our schedule marks are marked in 4 different categories. We have the winter break category, where we perform parts procurement and software development. Next is our manufacturing period, along with continued software development. Then we have our component testing and integration. And finally, the last section is the full integration test with our full vehicle. This is our budget. Most of our money is going into the airframe and electronics. And after tallying up all of our subsystem budgets, we come out to a little less than $3,700, which gives us a 26% margin in our budget. These are the people we'd like to thank for their support and guidance. Here's our list of references. Thank you for your time, and we are now open to questions.